In the last several videos, we've looked at examples of Lewis structures, and we've seen how useful they can be to represent organic molecules. They help us show connections, they help us show bonds, but unfortunately, we're going to find some limitations. Let's take a look at another example. Here we have the carbonate ion, CO3 2-, and when we think about valence electrons, we know that carbon has 4. Each oxygen has 6 valence electrons, so 3 oxygens gives us 18, and we have a -2, which means we add on 2 more electrons, giving us a total of 24 valence electrons. Now, as we draw our structure, we can have carbon in the middle connected to oxygen, oxygen, and oxygen. We know that carbon likes to have 4 bonds, so let's try giving this one a double bond. So we have 1 carbon-oxygen double bond and 2 carbon-oxygen single bonds. And now let's fill in the lone pairs to give everybody an octet. So this oxygen needs 2 more lone pairs. This one needs 3 lone pairs. And this one needs 3 lone pairs. Carbon has an octet, it has 4 bonds. Oxygen has 2 bonds, and it has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. So everybody's happy in terms of the octet rule. We also want to think about formal charge, alone minus own. When carbon is alone, so on the periodic table, carbon has 4 valence electrons. That's what we used here. And in this molecule, it owns 1, 2, 3, 4. 4 minus 4 is 0. Carbon has a formal charge of 0, and we don't have to write it. This oxygen has 6 when it's alone. It owns 2, 4, 5, and 6. This oxygen has a formal charge of 0. The oxygen on the bottom left, when the oxygen is alone, it has 6 valence electrons. In this molecule, it owns 2, 4, 6, and one of these, so it owns 7, which gives it a charge of -1. And the same thing over here, this one owns 7 electrons, so it has a charge of -1. So we would include our formal charge on our structure. So this is a valid Lewis structure for the carbonate ion. Looking at the structure, what does this suggest about the carbon-oxygen bond lengths? Well, if you can try to imagine having a single bond sharing 1 pair of electrons is going to be weaker and longer than having a double bond sharing 2 pairs of electrons. These atoms are going to be held closer to each other, so we would have a shorter bond length. So this suggests that we're going to have 1 short carbon-oxygen bond and 2 longer carbon-oxygen bonds. But experimentally, it's been shown that all of the carbon-oxygen bonds in carbonate are the same length. So we followed all the rules for drawing our Lewis structure, and yet what we've drawn does not reflect what actually exists. So let's redraw that Lewis structure, and we can have the double bond here, 2 lone pairs, over here 3 lone pairs, 3 lone pairs, the negative formal charge, and the negative formal charge. We also could have drawn it with a double bond here, or with the double bond over here. Now, all 3 of these are valid Lewis structures, but all 3 of them are incorrect. None of these actually exists because what exists, as determined by experiment, is some version of carbonate that has equal carbon-oxygen bond lengths. So what we have here is an example of resonance. This is a concept of electron delocalization. So rather than this pair of electrons being localized between this carbon and this oxygen, instead these electrons are distributed or delocalized further around this molecule. We are going to talk about resonance in more detail, but for now, we need to think about how do we represent this with Lewis structures? Well, we have to recognize that although this is a valid Lewis structure, and this is a valid Lewis structure, and this is a valid Lewis structure, none of them adequately represents what exists. We connect these through resonance arrows. This is a special type of arrow, double barbed at both ends. This specifically means that this is a resonance structure, and this is another resonance structure, and this is another resonance structure. So these can all be called resonance structures or resonance contributors. But what actually exists is going to be a combination of all of them. So we can draw carbon with a single bond to oxygen, single bond to oxygen, single bond to oxygen, but then we're going to have a partial double bond to each oxygen as well. So this is kind of an average of all three of these resonance contributors. In terms of formal charge, we can specify that this has a partial negative, and a partial negative. Now, this structure is consistent with experimental evidence. If all of these carbon-oxygen bonds have the same amount of partial double bond character, then they're all going to be the same length. And notice that also results in the partial negative charge being distributed equally on all three oxygens. So this is called the resonance hybrid. We're going to talk more a little bit later about resonance. For now, I want you to consider the possibility that there are multiple Lewis structures that can be drawn for some compounds. I want you also to consider the fact that while these are representations, none of these actually exists, and the hybrid is what actually exists. So if you had a way to take a snapshot, you wouldn't have a snapshot where you have some molecules like this and some molecules like this. None of these exists. All of the molecules will exist more like this. We don't have this pair of electrons localized between this carbon and this oxygen. Instead, these electrons are delocalized around all three carbon-oxygen bonds. We will come back to this concept of resonance of delocalized electrons later in this chapter and throughout the year.